our previous course material, please let me know. So last time we started to learn about photonic crystals, right? So, and then if I briefly recap what we learned last time, photonic crystal has been inspired by the naturally occurring crystals like atomic lattices. And this atomic lattice, like due to this atomic lattice, the electronic band structure occurs, and they have specific momentum energy relation, dispersion relation. And similarly, people thought that maybe if we have a periodically placed optical structures like periodic, basically a dielectric films or 2D or 3D periodicity, we can have a band structure for photons, right? And then understanding this is actually a pretty straightforward thing. And in order to understand this phenomena, we began with Bloch's theorem, right? So Bloch's theorem tells us that if you have a periodic potential or periodic dielectric function, then the solution of the wave, the solutions of the wave equation, like electric field and magnetic field, should satisfy a certain relationship here, shown here, right? So your electric field and magnetic field must be a product of a periodic function and e to the ikr, right? And then we proved, this Bloch's theorem. And then we introduced about a few definitions about lattice. So Bravais lattice is just a infinite array generated by a set of translation operations described by primitive vectors like A1, A2, A3 in this case. And we also defined the reciprocal lattice, which is basically a Fourier transform of the real lattice, right? And then we define Brillouin zone in this reciprocal space or K space, just the area or volume occupied by a specific grid point, lattice point in K space, right? And then what we've done, I guess this from here was important. Like we just started to actually try to solve 1D photonic crystal. So here 1D photonic crystal is just the alternating layers of dielectric and different dielectric materials having a periodicity A. And then by Bloch's theorem, we know that the solution must satisfy this relation. The electric field at position R and electric field at position R plus AZ should be related by a e to the ikZA, right? So that's what Bloch's theorem says. And then we introduced the concept of transfer matrix in order to solve this 1D crystal. So the transfer matrix connects electric fields in one side to electric field on the other side. So E1 plus is the electric field of magnetic wave, electromagnetic wave, going on to the right direction. And then E1 minus is the electric field of the wave escaping from this side. And then E2 plus and E2 minus are defined in similar ways. And then the transmission matrix or transfer matrix M basically connects E1 plus E1 minus to E2 plus E2 minus, right? And then we can easily get transfer matrix equation. And then if we have a multiple layers or multiple optical components placed in series, then we can just simply multiply the transfer matrices in order to get the response of the entire thing. So we apply this thing to our alternating layers of dielectric materials. So we began with this propagation, basically the propagation matrix, which just gives you a phase advance, right? So phase along positive direction, phase along negative direction. And then we also introduced this boundary matrix, interface matrix. So this just tells you about the transmission and reflection at the boundary. And then once we combine these two, propagation matrix plus interface matrix, we get another like combined transfer matrix of this region. And then we do the same thing for alternating layers. So now if we include a one period of our alternating dielectric slab, our transfer matrix is defined as P1, I12, P2, I21. Okay, so P1 here, and then I12 is interface 1 and 2, and then P2 is the propagation here, and then I21 is the interface 2 and 1, right? So if we do that, we can get the transfer matrix, and then this transfer matrix, by definition, connects the electric field in this side to the electric field on that side, right? EM plus EM minus on this side to EM plus 1 plus EM minus 1 plus, M plus 1 minus here. And then Bloch's theorem also connects these two electric field components, right? This is just what we learned before. So the only thing left is that if you compare these two equations, they look exactly same, but one difference is that here in the matrix equation, this is a matrix, and then in this equation, this is just a scalar number, right? But we do know that this equation is satisfied, and this is our eigenvalue problem. So now we can combine this equation in this manner by just scalar times identity matrix, and then here is another matrix. So this is our eigenvalue problem. So in order to have a non-trivial solution, this matrix in front should have a zero determinant, right? So from that condition, we get this relation, which is which connects the the material properties and the thickness to and the frequency and the momentum of the waves resides in the system, which is dispersion relation. So if we draw it, that's the dispersion relation, and then we do know that if the epsilon1 and epsilon2 are different, then we start to have a photonic band gap where there's no propagating mode exist. Okay, so that's what we learned. And then in order to understand what's actually happening at the, let's say at this frequency where the at the top of the valence band and the bottom of the conduction band. Well, this is not a conduction band nor valence band because this is just a photonic band structure. So there's no interpretation such as a conduction band and valence band. But anyway, we can make an analogy to understand what's going on. And we learned that in the lower band, most of the energy, most of the electric field basically lies in the high index medium. So if you have more energy resides in the high index medium, your entire frequency gets lower. So this is the lower band, and in the upper band, most of the electric field actually lies in the low index medium, right? And then if you actually compare how much of energy resides in the high index medium, you can see here the concentration factor is much higher in this case compared to that case. Okay, so this is what I told you last time. So do we have any question so far? Okay, Jung Myung-gun asks how epsilon and potential is related. So you can, in order to understand that, you should see the comparison between quantum mechanics and electromagnetic system. So this is our quantum mechanics, and this is our, the Hamiltonian for our electromagnetic system. And you can see here, VR is the electric potential, right? Whereas we have 1 over epsilon in this operator. So it's not exact like 1-to-1 match, but you can imagine that high potential means low permittivity, right? Because we have 1 over epsilon here. So if we have a large potential and small potential like up and down, this corresponds to the opposite pattern, like epsilon small and epsilon large, right? So that's basically a simple analogy that you can make. So for those who are not familiar with like physics or solid state physics, maybe making this analogy is just makes you even more confused. So if you feel this is very confusing, just making analogy between like solid state physics and electrodynamics is confusing, then you don't need to rely on this thing. You can just ignore this part. Okay, it's not, this part is not that important. The only thing you need to understand is this part. And then I guess our derivation actually does not rely on any quantum mechanical aspect. So you don't need to worry too much if you don't understand the analogy. Any other question? Okay. Well, then we should also start to talk about photonic crystals, like Olfex's response of photonic crystals. So when we did this analysis, like remember that we have, like, let's say we have 1D photonic crystal, N1, N2, N1, N2, and so on. Then we set our K vector is along this direction, right? And that's why, that's how we set our propagation matrix as e to the ikga, right? It's like kgd, for instance, if this is d, right? But here what we draw as a dispersion relation, this k vector is along kz, the propagation direction here. Okay, but of course there are possibilities that you have a photonic crystal, and then light basically impinging with non-zero angle of incidence, right? So that your light, the incident light has non-zero k parallel component, for instance. So what's gonna happen in this case? So to show what is happening, we basically draw this plot, okay? And here we show that what's happening when ky, so this is y direction, when ky becomes non-zero. And then one thing that you can immediately notice is that as you go to a non-zero ky, you start to have two different bands, right? So here, if you look at when you are only changing kz, blue and red curve are coincide with each other. But as you go to ky non-zero, they become deviates from each other. And the reason is when you have a non-zero like angle of incidence, then now you need to start to think about the polarization. So like in normal incidence, it doesn't matter whether your electric field is this direction or that direction, because they have symmetry, the system have symmetry. So the rotation along z-axis doesn't affect your result. But in this case, when the incidence is non-zero, angle is non-zero, then you should take care whether your electric field is along this direction or that direction. I mean, these two are different in this case. So that now you start to have different response for TM and TE polarization. And I'm not sure what is n equals 1 and n equals 2 in this case. I guess this is just this is just a TM and TE. Okay. Right. And there's another aspect. Even though I told you that, let's say we have a band gap here, for instance, here, okay, in the yellow regime. What I said was that we have no propagating mode in the yellow region, right? There's no propagating mode in the yellow region. And that is true, but that doesn't necessarily mean that there's absolutely nothing in between, in the band gap. So in the band gap, what happens is that if you draw the dispersion relation, not only in the real k-axis, but also in the imaginary k-axis, then you will realize that they actually have some state, but in here, your k vector is purely imaginary. So you see the red curve, it just showed you that in the band gap region, you have a mode, but in there your k vector is imaginary. Okay, so what does that mean? What does that mean? Like, what does what does it mean by saying that you have imaginary k vector mode? So in order to understand that, you should think about this. Like, when you talk about like k vector, you should always imagine e to the I k z, like this function, okay? So when your k vector is real, then this function is oscillating, right? So real k vector means oscillating mode, like propagating mode. So now you understand what is imaginary k vector means then. When k vector becomes purely imaginary, then this thing becomes e to the minus kz, like just a exponentially decaying function, not an oscillating function. So imaginary k vector means that you have a mode, but it's not gonna propagate, but it exponentially decays as you go deeper. right? And what's the implication of it then? So why do we even care about it? Well, we do care about it because it can mean something interesting. Like for instance, at the surface, let's look at the surface of the 1D photonic crystal. And at the surface, we can imagine a mode confined on the surface, which is exponentially decaying as we move away from the interface. Like in this plot, okay? And this mode, even though it cannot propagate along z direction, this mode can propagate along surface parallel direction, right? So this is a surface mode. Okay. And also, if we have a defect in the lattice, like a crystal, so it's like a N1, N2 keeps going on, N1, N2, N1, N2. And then what I mean by defect is like either N is different from like N1, N1 or N2, or maybe its thickness is different from the other crystal parts. So that this is called defect. And when we have a defect, in this case, the defect is different thickness, right? So if you look at the crystal part, you have like alternating layers of blue and green with the same thickness, like repeating thicknesses. But here in the middle, the green part has a wider thickness compared to the others. So this is called a defect in this case. And when you have a defect, this defect support a localized mode. And this localized mode exponentially decays as it moves away from the defect point. And that also can be explained by this imaginary K-vector mode. Okay, so how to explain this? Well, you can explain this in that way. So let's say your omega is in this regime. Then, the crystal part, you shouldn't have any propagating mode, right? Because it doesn't exist. So the only possibility is you have a decaying mode, exponentially decaying mode, which is actually looks like this. So you have exponentially decaying mode in this way, and you have exponentially decaying mode in that way. And in the middle, you have a defect so that this mode can survive, right? So that's another implication of the evanescent state. Okay, so this is it about a 1D photonic crystals. Do we have any question? So even though this is 1D, it basically contains almost everything we need, that is required to understand photonic crystal. So how can we excite the defect mode? This is a good question. The way we excite defect mode, and there are many ways, but like one thing that you can think of is like you can put on for instance emitter here, like light emitting molecule, for instance, and then you shine light from the outside, and then because the excitation light has different omega, so there's no way, there's no problem this excitation light penetrating into the medium. And then this one excites the emitter. The emitter emits with a lower frequency omega, which is probably in between this band gap. And then you can basically excite this mode. And there are many other ways. There are many different ways to excite defect mode. For instance, you can also think of, say, you have a defect mode here, and then your photonic crystal not goes all the way to the infinity, but you basically cut it at certain point. Then, if you shine light from this end, then even though it exponentially decays as it penetrates into the photonic crystal, it still has some overlap with this defect state, so that you can also excite this mode. So there are many ways to excite defect mode. And then this defect mode is actually, it's the most important the application of the photonic crystal. So people create cavity, optical cavity with high Q factor with this defect mode. But this is a really good question. And do we have any other question? Okay, then. And then let me move on to the 2D photonic crystal. So from now on, my explanation would be mostly hand wavy. I'm not gonna write complicated equations in order to prevent any confusion. Okay, but the basic physics is basically same as 1D photonic crystal. Okay, so let's move on to 2D then. So a simplest form of 2D photonic crystal is a 2D array of dielectric cylinders. So here the blue cylinder is the dielectric cylinder, and then here A and R defines the spacing between the dielectric cylinders and the radius of it. And if you draw dispersion relation of dielectric cylinder, you can see the TM mode, the blue curve, have a band gap. Right here, TM mode have a band gap, whereas TE mode has no band gap. Right? So that's one thing that you can notice immediately. And another thing you can probably notice is that we have this characters that wasn't appeared in our previous 1D problem, right? Gamma, X, M, gamma. Okay. So now you think about, if you think about the 1D photonic crystal, this was your real lattice, right? So it's separated by A. And then your K space also looks like this 1D thing, so that your Brillouin zone is just 1D, right? 1D in K space from pi over A to minus pi over A to plus pi over A. So there's, all you need to do, if you draw the omega versus K, then your K is well defined, only have one direction in 1D photonic crystal, right? But in this case, you have 2D lattice, so that your reciprocal space is also 2D. So your Brillouin zone, so your K space also looks like this. So your Brillouin zone is just a square in K space. So in order to draw the dispersion relation of 2D photonic crystal, what you need to do is actually you draw Kx, Ky, and omega. So it's like a 3D plot, right? So that's how you obtain the band structure of 2D photonic crystal. But it's kind of too complicated, right? Like if you draw something, in 3D, it's kind of difficult to visualize. So instead, what people do is people just draw the dispersion relation along certain line, specific line in K space. So that's this. Gamma point is the origin in the K space, and then X point and M point are defined in this specific way, and then here the M point and X point gamma point are called high symmetry point because they have like high symmetry. Okay, so instead of drawing everything, you are just drawing these three lines. So gamma to x is basically drawing from here to here. And then x to m is drawing here to here. And then from here to here, you draw to there. So you can realize that the length here, gamma x and xm are same, whereas m to gamma are longer, right? Because it's just you can see it's obvious in the Brillouin zone diagram, right? So now we understand, we try to understand why a TM polarization have band gap, whereas TE mode doesn't have a band gap. So to understand that, let's look at this field plot. So here, I don't want to go into too much detail, but I just want to give you some just a very general understanding about this phenomenon. As I said, the omega difference of a top of a lower band and the bottom of an upper band is determined by how much of energy is concentrated at the high index medium. So if this concentration factor differ by a lot, then you have a relatively high K vector. I'm sorry, a high band gap, and if there's not much of a difference, then the band gap becomes smaller or even closed. So having that in mind, if you look at the D field, basically D field is also in electric field of the TM field, TM polarization at position X here, position X, right? This position in the K space. So in the band 1, the lower band, most of the electric field is concentrated on the cylinder center, right? Whereas if you go to band 2, so band 1 and band 2 must be orthogonal. So if you look at the band 2, now you have a node. What I mean by node is like 0 electric field position lies along the cylinders, and the maximum electric field position basically in the middle, in between. And of course, because they have a high index contrast, if you actually measure the D field, they are actually highest in the cylinder. But anyway, if you calculate the concentration factor, which is defined as the total energy versus the energy confined in high index medium, for TM polarization, band 1, dielectric band, has the concentration factor of 83%, which means 83% of electric energy is confined in the cylinder. Whereas in this case, because electric field node exists at the cylinder, so the concentration factor dramatically drops to 32%. Okay, so because there is a huge difference in concentration factor, we can kind of associate this to the large band gap in TM field, TM polarization. And for TE polarization, if you look at this, TE polarization, I just draw the H field instead of an electric field because it's kind of difficult to draw the electric field is difficult to recognize. So you can just think of a derivative of H field is proportional to the E field. So now you have H field here, and then you can think of like taking basically the gradient or derivative of H field so that you can get the E field. Okay, so now if you look at this, now H field has node at this point, and the and in the cylinder point, and in band 2, the node exists in between the cylinder position. So the overall thing is similar, but if you actually calculate the electric field, if you take the derivative of H field to get the electric field and calculate the electric energy, then you realize that electric field concentration factor of the band 1 is actually pretty low. It's only 23%. And then error band, it's even lower, because if you think about the derivative becomes maximum here and minimum there. So it's like if you do it, it's 9%. So because the difference in concentration factor is low, we imagine the band gap is actually also gonna be small, but in fact, it's actually, there's no band gap. Okay, well, there's a small band gap here to here along x position, but like overall, there's no band gap. Okay, so again, this is not a how can I say, rigorous way of explaining things. I'm just giving you just hand wavy argument why at certain polarization you have a high band gap, and the other polarization you have a small band gap or no band gap. And things are going to be more clear if you go to the next example. So the next example is this. Okay, now you have a different type of photonic crystal, which looks like a fishnet. It's not like a cylinders, but it's like a connected fishnet. Okay, and then here you realize that things are exactly the other way around. Like electric TE mode now have band gap, whereas TM mode have no band gap or very small band gap, right? So why this is the case? So let's look at the field profile again, like the same thing as we saw before. So in this case, if you compare these two, band 1, obviously, most of the electric field is concentrated at the center bar here, right? And in band 2, one big difference is that now you have a connecting bars, so that even for band 2, your electric field are still concentrated in the high index medium. So the concentration factor is not that much different. Okay, so if you want to make a contrast here, in this case, if we have a separated cylinders, the concentration factor for the band 1 and band 2 are very different, because in band 2, the field maximum is supposed to be in between the cylinder region, but there's no high index medium in between. So that we have a high concentration factor difference. But here in this case, band 2 have electric field maximum in between the bars. And fortunately, you have like crossing bars, which have a high electric field concentration. So the concentration factor are not that much different, so that you don't have that high band gap. Okay. And on the other hand, if you look at the this case, the TE case. Now imagine again, because I draw H field, you should think about the derivative, like along derivative of the H field in order to imagine how your electric field is going to look like. And now, if you look at the band 1, you see here the H field node is located along the fishnet, the vertical bars. And because your derivative, like if you take the derivative of the H field, it becomes maximum along this line. right? Because if you take the h derivative along x direction, it's gonna be maximum, right? So in this case, band 1, you have a high concentration factor. But here, if you look at the band 2 diagram, you see your derivative maximum lies along this line. So only this part, and this part, like small portion of the structure, you have a concentrated field, right? Here, only here. Electric field is concentrated in the high index medium, whereas in this case, this entire thing's electric field is very high. So the concentration factor contrast becomes larger in this case. So TE have a large band gap, TM have small band gap in this case. Okay. And people try to find how to create band gap for all polarization, right? Because if your band gap depends on like polarization angle, then it's not too much useful. So they just try to create band gap in all angles so that you, no matter what polarization you shoot for, you have a band gap, and so this structure, basically inverse cylinder structure. So you have high index medium here, low index free space cylindrical shape in this part, have a photonic band gap, like full photonic band gap, regardless of the polarization. Okay, so if you look at this, this is kind of a combination of this and that, right? It's not like just a connected fishnet, and also it's not just a concentrated dots. It's more like in between. You have some concentration points, but they are connected, so that you have band gap in both TE and TM polarization. Okay. So we can also, the 2D photonic crystals can also have defects, like you can think of surface, line defect, and point defect. So if you begin with point defect, like you have like photonic crystals everywhere, like this, but you have a one cylinder that is different from the others. Okay, so this plot shows you what is happening. Like here, this is the dispersion relation, and I'm sorry, the y-axis is the frequency, and the blue region is where you have a propagating mode, and then yellow region is the band gap region. So in the band gap, of course, there's no propagating mode, but x-axis is the defect road radius. So the original radius is 0.2a. So here is the perfect crystal. Okay, you can see here, if there is a perfect crystal, there's no mode, no propagating mode or whatever in the point defect. But as if your point defect becomes smaller than the original radius, then you start to have a monopole mode, which looks like this. Monopole mode is that you have a like monopole, like plus and minus oscillating here in between, like monopole. Okay. And you realize that here R equals 0 means there's no rod at your position, which corresponds to this point. And now, if your cylinder is actually larger than the original cylinder, you start to have a higher order modes. So if it's 0.34a, which is like somewhere here, then now you have a dipole mode. You see here, plus minus. So there's a plus minus oscillating. This is dipole, right? Dipole mode. And then if you go to a 0.55 here, you now have a quadrupole. So quadrupole means like you have 4 poles, plus, plus, minus, 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 plus, plus, and so on, right? And here you also have monopole 2. Here's a monopole 2 mode. It's a second order monopole mode. The difference between the first order monopole mode and second order monopole mode, you can realize that here the first order monopole mode, the oscillation along this direction, the oscillation along this direction is very slow, right? Up and down and up and down. But here, monopole 2 mode has high oscillation, like even inside the cylinder. So it's like higher order mode. They are same monopole, but actually, if you look at the radial direction mode index, this mode index is higher than this mode index. So that you have a second order monopole mode, and so on. So you go to 0.7, you have a hexapole, and so on. Okay, so depending on what kind of defect you have different type of different type of mono oscillations, localized oscillations. And then if you have a line defect, similar thing. So so to show the line defect, I just draw the dispersion relation, like a frequency as a function of wave vector along this direction, k direction. And then blue again is where you have a propagating states. Yellow is a band gap region, and you can see if you have a line defect, like there's nothing here, then you have a guided mode along that line, which looks like this. Okay, so as I said earlier, even in the band gap region, if you think about this k vector, they have a imaginary k vector mode. Like it's not propagating, but there's an evanescent mode exists. So you can see here in the photonic crystal regime, you have a exponentially decaying mode, and which is localized along the point defect, line defect. You can see here, there's nothing. There's supposed to be dots here, but there's nothing. So that this is a defect, and this mode is propagating along this direction. Okay, or in this plot, it's along that direction. So we can create a waveguide using the point defect, line defect in the photonic crystal. And then surface defect, the same story. So like if you have a crystal and which have an ending like this, and then you have an air interface, then what I draw here is the same thing, the dispersion relation, and then this pink region is where you have a propagating mode, photonic crystal mode, and then this red line is the dispersion relation of the air, like air, and then you can see that this green line, which shows the surface mode, surface propagating mode, which exists outside of the light cone and also inside the band gap. So you can see here, this mode, you can have a propagating surface mode along the interface. Okay, and this mode is supposed to have a high k vector. Okay, so this is how you use a defect of photonic crystals. It's same as 1D photonic crystal. It's just things are becoming 2D now. Okay, so what about 3D? If you go to 3D, things are of course even more complicated, right? Now you have like 3D lattice, so that your Brillouin zone also becomes 3D, like in this figure. Where is it? This figure, right? Your Brillouin zone is 3D. So if you want to draw your full band structure, you should draw omega as a function of kx, ky, and kg, right? It's like 4D plot, which is, you know, difficult to draw. So instead, again, we just draw the dispersion relation along the high symmetry point, gamma, k, w, x, u, l, like, and so on. So if you draw that, yeah, this is an example. You can see here gamma, x, w, l, u points, so high symmetry points, and then this, you know, this interesting looking photonic crystal is called yavlonovite, okay, which is invented by Ilya Yavlonovich at 1991. So Ilya Yavlonovich is a professor at UC Berkeley who kind of pioneered the field of photonic crystals. So he's one of the inventor of a photonic crystal. He is actually still active. He's still active researcher in UC Berkeley, and this is the his first theoretical calculation of full 3D photonic band gap, like, which is, so that's called Yavlonovite. He's following his name, Yavlonovich. And later, people also came up with another different structure, which is called inverse opal structure, which can also experimentally fabricated, and which has also a photonic band gap here. So there are many different versions of 3D or 2D photonic crystals that people experimentally realized. Okay, so just to give you, so before we move on to the applications of photonic crystals, I just want to give you like one more concept, which is a diffraction. So like if you have a periodically placed materials, like you have like one line of material and the other line of material, then you can think of a reflection of light on the top layer and the reflection of light on the next layer, neighboring layer. And if you compare the propagation length difference, seems like if you draw this line and if you draw that line, so up to this point and from this point, their path lengths, the first layer and the second layer of light path lengths are the same. So the path length difference is actually given by this two, right? Which is the, sorry, you know, yeah, this A is supposed to, this is supposed to A. So it becomes 2A sine theta. So if this path length difference is an integer multiple of lambda, which is like in this case, you can see here, they are constructively interfere with each other. So you can see if you look at the phase here, they are the same, right? They are the lowest point. So these two waves constructively interfere with each other, okay? Whereas when this becomes a half integer multiple of lambda, then you see this one and that one are destructively interfere with each other. And even though it's not like a destructive interference, if there's many layers of this and then there's no constructive interference occurs, then eventually it's gonna go away. So the diffraction condition is determined by this. This is another interesting phenomena when you have a periodic optical materials. So now you can understand what's going on at the interface between your photonic crystal and air. This part is not necessarily, I mean, it's not that important, but I think it's interesting to understand. So let's imagine what's happening like in typical materials. So like if you have a typical material and you have light impinging, then you have a reflected light and then refracted light. And then if you think about K vector, this is gonna, you know, it's gonna look like this. It's like a in-plane K vector are preserved. And then if you think about the energy flow is also be similar, like energy flow is kind of same direction to the K vector direction. So nothing special here. But in photonic crystal, things can be different. So let's see why. So if you look at, yeah, this plot is not too easy to understand, but anyway, this is Kx and this is Ky. And now, you know, this is your incident light. So here's the gamma point, 0 K vector, and incident light having this K vector, for instance. Right? And then its surface parallel component is this. Right? And then we know that when reflection and refraction transmission happens, surface parallel component of K vector must be preserved, right? So your reflected light and transmitted light, all of them have a surface parallel K vector, same as this amount, right? In other words, your reflected light and refracted light must lie on this line. Okay. And now what's interesting is that in the air, right? In the air, if you draw the dispersion relation of the air, it's K and omega having this shape, right? Because omega is CK, or there may, yeah, omega is CK. So it's just a linear line. And if you think about Kx and Ky, it's just the omega is equal to C Kx squared plus Ky squared, which is just a circle. So if you cut through at a certain omega, your air dispersion in K space, Kx and Ky space, must be circular, right? So you can imagine you just cut through this dispersion relation and it becomes circular, right? And then now let's look at dispersion relation of photonic crystal. So if you look at the dispersion relation of the photonic crystals, they are very strange, right? It's not just a cylinder. It's, you know, for instance, in this case, you have a peak at gamma point, and in this case, you have a peak at K point, and so on. So the dispersion relation of the photonic crystal can be very different from free space light. So now you go back to this case. You can imagine that at that frequency, that specific frequency, your dispersion relation crosscut looks like this, like a circle around M point. It's like, go back to this again. So let's say this is your M point. So this is your M point. And then imagine you cut it through here. So this was your omega. then you probably have, so if you imagine like how it's gonna look like, how its cross-section is gonna look like, you probably have some states around M point, but there's nothing around, right? There's no other states. So that's the situation. Okay, so if that is the situation, then this is your incident light, K vector. This is your reflected light, K vector, right? Because that's the only solution. Because this has to be preserved, your K point must be lie on this line, so that now you have this K vector allowed for refracted light, right? So in terms of K vector, it should look like incident, reflected, and refracted based on this. But the thing is, I'm not gonna explain you detail, but your group velocity, how the energy flow goes, is actually is proportional to yeah. Well, I already explained actually. Your group velocity is related with this d omega dk, right? And then if you have a multiple k direction, it should be gradient of omega. And then gradient of an omega must be perpendicular to the how can I say, frequency line, right? So if you think about the group velocity direction, here in this case, in the air, the K vector direction and the group velocity direction are the same. But here in the photonic crystal, your K vector is along this direction, whereas your group velocity is going this way because it's perpendicular to the dispersion line. So to sum up, if you have a photonic crystal, your incident light and reflected light are just as usual, but you can have a negative refraction. You can have a electromagnetic wave energy propagating along that direction. So you have negative refraction, which was also an interesting point. Not sure whether this is easy to understand, but anyway, I kind of tried my best to convey this idea. Yeah, so next time we try to learn about some of the applications of photonic crystals. And right, so this is it for today.